Whiteboard Physics A-Level Lesson 71. More circuit calculations. And now we're interested in two situations. One is where there's more than one cell. What do we do about that? And the other one is where we have diodes in circuits. Let's start with more than one cell. And remember that our cells have internal resistance. Now, what if the cells didn't have internal resistance? Let's start with that. If cells did not have internal resistance, then what? Then if I had a power supply that consisted of, let's say, 3 cells in series, just like that, and this was epsilon 1, this was epsilon 2, and this is epsilon 3, then the potential difference between this point and this point, remembering Kirchhoff's second law, would just be equal to epsilon 1 plus epsilon 2 plus epsilon 3. That would be nice and easy. And if we had cells in parallel, so let's say we have, let's give myself a bit more room. Let's say that I had a cell here, a cell here, and let's have another one here, because why not? So here's my parallel cells. You can use a ruler for diagrams. I don't know why I'm being so lazy in all of this. Epsilon 1, epsilon 2, epsilon 3. This is where it gets a little bit more complicated. But if this is all we've got to go on, then it wouldn't be possible to have that situation and not have it so that they're all the same potential difference across them because of Kirchhoff's second law. And we know we've got to start and finish at the same potential within a loop of a circuit. So we know that in this situation, V would have to equal epsilon 1, which would have to equal epsilon 2, would have to equal epsilon 3. And then you may be asking, but what if I put batteries in that have different EMFs? You know, I get a 1.5 volt battery and then a 6 volt battery or a 9 volt battery, and I put them in parallel with each other. What will happen? Well, we'll come to that in a second. But the point there is that you're talking about real batteries, and real batteries have internal resistance. If we say, well, we've got an imaginary battery with no internal resistance, and we say, well, I'm going to take these 2 imaginary batteries with no internal resistance and I'm going to connect them in parallel with each other, we've created an impossible situation within the physics. And then we're asking, but what happens in this impossible situation? Well, syntax error. I can't answer that. You're asking me to solve an impossible problem because you've made an impossible problem. So let's go slightly differently. Let's talk about when we do have internal resistance. Let's make the problem possible. So if the cells do, if cells do have internal resistance. And let's start with the cells in series. Now, there's a lovely principle that we refer to as circuit topology. Circuit topology is about how components are connected together, in what order, and so on. And although this would not be topologically identical to this, in terms of the circuit's functioning, actually it functions in the same way. You can see what's going on here. Now, if we go back to the old diagram of the roller coaster, and I don't want to show it again, I keep showing it, but if we go back to the old example of the roller coaster diagram, then we can see that from the very start to the very end, in both of these situations, we would have, how can I not write the number 3 properly? We would have descended the same or ascended the same potential difference. So we've got here our I, R1, our I, R2, our I, R3. I'm only including the I because that way it's all potential differences. If you use a different color or some sort of other symbol, then you can make it clear that you're only interested in the resistances. But there we go. I, R1, I, R2, I, R3. They'll function in exactly the same way. So if I take my voltmeter and put it in series, in parallel with these series connected power supplies, these series connected cells, with each one having its own internal resistance, then what do I get? Well, in this first example, I have a potential difference equal to epsilon1 plus epsilon2 plus epsilon3. I've gone up those amounts, but then I've gone down minus IR1 minus IR2 minus IR3. I've dropped those potential differences across those internal resistances. Okay, fine. What happens in this right-hand example? Well, it's absolutely no different. In fact, I might change the way I've written the one on the left just to make it clear what's going on. Minus IR2 minus IR3. Let me change the way I've written the one on the left. Yes, when you make notes along with me, you might have to make sure you can erase things or pause the video at various points and make sure I haven't gone back and changed things myself. On my website, I'm making all of these notes available to download, which you might find helpful, you might not. And they are identical. These two situations, they are the same. These circuits, they behave the same way. And that can be really helpful because we know that when I have 3 resistors in series, I can replace that with a single resistor that does the same job. So now what I can say is this is exactly the same as this. And hopefully I've given myself enough room here, whereas that is epsilon1 plus epsilon2 plus epsilon3. And this is I, R1 plus R2 plus R3. We've added the 3 resistances together. And when I've done that, the potential difference across it, V, like that, is going to be exactly what we thought it would be. So all we've done is combined those resistors into a single resistor, as we already did earlier on. And we combine the power supplies into a single power supply. So let me just make a little note of that. We can does it say in series at the top of this? No, but I better make a note of this. In series, we can simply, I say simply because I think it is simple, simply add together EMFs and combine internal resistances into a single resistor. And there we go. So that's in series. I think that's very straightforward. The power supplies don't have to have the same internal resistance, and the power supplies don't have to have the same EMF. They can be different. But what about in parallel? Because we've said, in parallel there's no internal resistance, then the idea of having different EMFs in parallel is just nonsense. I can't make sense of that. Sure, but what if I use real power supplies, real cells? What then? Well, okay, let's sketch it out. And I will sketch it out like this. Starting with, actually, let's just make a little subnote here saying in parallel. Just like this. And we will try to do this let's just do 2 cells to start with, rather than doing 3 cells and getting ourselves in a muddle, because it is the same, it's just a little bit more involved mathematically, but it's the same principle. So if I have 2 cells in parallel and they happen to have internal resistances. So remember, when we're doing our physics, if there's an exam question, it says that there's no internal resistance, or the internal resistance can be ignored, and our power supplies are in parallel, they're the same EMF. We don't add them together. It's exactly the same. Don't make that blunder. In series, we just add them together. But in parallel, if there is an internal resistor, then we will undoubtedly have identical cells. They don't have to be, but we will undoubtedly, let's go with 3, but let's say they're identical. If they're not identical, we can look at what that means in a bit. But let's start with 3 identical cells. So let's make a little note here. Assume identical. Assume identical cells. And so what we've got is epsilon, 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 and IR, IR, IR. They're all identical, so I won't bother using the subscript 1, 2, and 3. And our terminal potential difference, what's that going to be? Well, now this is the interesting thing, because if we picture this as 3 different branches on a roller coaster, then we know at these points that I'm colouring in with orange here, here, and here, at those points here, the potential will be the same. We know the potential has to be a particular value over here on the left, and we know the potential has to have a particular value over here on the right. But also, because it's the same EMF for each of these, then any charge passing through from right to left will ascend the same electric potential as it goes. And actually, that's really helpful, because if any of these 2 orange points are at the same potential, then their potential difference between them is 0. And how much current flows through a wire if the potential difference across it is 0? Well, nothing. No current flows through it. So we could say here are all at same potential at that point. So if we connected a wire there, it wouldn't make a difference to the circuit. And I'll just say that. If wire connected here, no change to circuit, because no current flows through the wire because there's no potential difference across it. It's not always the case, actually, but that's good enough for now. So if we did connect a wire across there, we would have 3 EMFs in parallel with no internal resistance. So it's just epsilon. And then we'd have 3 internal resistors in parallel, and they're identical. So the combined internal resistance would be calculated using that lovely formula. Let's say RT, the combined one, is going to be the reciprocal of the sum of the reciprocals of the internal resistances. And because they're identical, we can even make that even easier in a second. So the sum, n equals 1 to however many there are. In this case, there are 3. R, n to the minus 1, all to the minus 1. And if you do that, what you find is that if you've got 2 resistors, then, and they're identical and they're in parallel, the combined resistance is half of what it was. You've got 3, it's a third. So in this case, we could say that RT is just equal to a third of R. That's what's happened. That's what must happen. And that kind of works as well, because we've got these 3 branches. So the current going through each of these is going to be a third of what it would have been. So we've got a third of the lost volts. And how do you get a third of the lost volts? Well, one way of imagining a third of the lost volts is to have a third of the internal resistance. So it does all follow quite nicely. So in this case, your V would be equal to, in this case, epsilon minus a third of IR, because there are 3 of them in parallel. And if there were 4 of them in parallel, it would be minus a quarter IR. And if there were 5 of them, minus a fifth of IR. Great! What if they're not identical? Well, if they're not identical, and that won't come up in your A-level, then what we have to do is apply our Kirchhoff's laws separately to each. That means Kirchhoff's first law and Kirchhoff's second law, Kirchhoff's first law at every junction, Kirchhoff's second law across every component. We end up with a big nasty set of simultaneous equations, and when we work our way through those simultaneous equations, we may well find that the current passes backwards through a power supply. Well, power supplies might not work very well backwards. It could cause some sort of heating effect. It could cause batteries to explode and all the rest of it. I don't know, I'm not an electrochemist. But that's why you don't connect in parallel batteries that have different ages, because then the internal resistances are different, which means that they won't have the same potential at that point, which means that some of the batteries that you're connecting into your appliance, the current will be going the wrong direction through the battery, potentially. And that would be dangerous. It doesn't have to. It might just be a different amount of current passing through it. But in an extremis, it could be current passing backwards through the battery. Now, there is another way of solving problems with circuits where we've got multiple power supplies in parallel and they're different power supplies. And that's by using the principle of superposition. I did a couple of videos on superposition, which, again, let me know in the comments if I forget to link it in this video, which I'm sure I will, and I'll add the links into the description. I'm bound to forget. But yes, you could also just search on YouTube, on my YouTube channel, for superposition to solve circuits. And there's short videos that will show you how to do that. It's a really handy technique, quite an advanced technique. It's really for students who are heading for the B's, A's and A stars at A-level. But everyone should be aspiring for that. And it makes it much quicker and easier to solve circuits problems if you know superposition as well. But I'm not going to cover it in this lesson. I would cover it in my school because I teach very, very advanced students. I'm a selective school, and in order to get in, they have to have already got a grade 7, 8 or 9 at GCSE. So they tend to be very clever. We rattle through the specification quite quickly to make sure we have time to do things like superposition. And there is, as I say, I've recorded the video to help you. I'm not cutting you off. The video's out there for you, but I'm not going to cover it in this series because it's quite an extra bolt-on thing. Right, the last thing I needed to talk about was how to handle diodes. And I'm now looking at this and thinking, crumbs, I don't have a lot of space for diodes at all, do I? So I'm going to have to cram diodes in down here because I only wanted to use 1 page of notes per lesson, really. So let's cram diodes in here. Diodes. Now, if you remember our graphs of the characteristics of components, which I think I did back then, yes, that lesson back then, I don't know which lesson it was, characteristics of components. It was the lesson titled Components and Their Characteristics, unimaginatively. With a diode, we had this characteristic on the right, where we had pretty much no current at any potential difference below about 0.6, 0.7 volts. And then there seemed to be very little impedance to current, very, very low resistance at much higher potential differences. In fact, you can't get to higher potential differences than maybe 0.8 volts. So you keep on increasing the potential difference across a circuit. The diode only takes across it only drops about 0.8 volts. It's really hard to get it to drop any more than that. So actually, one way to handle a diode is to treat diodes like sources of EMF in reverse. Let me explain what I mean by that. So this is only for what we call forward bias diodes. So forward bias diodes are those where they're connected in the direction that current can conduct. So forward bias is when they're connected with the diode in that position and the positive and negative. We treat the diode like a power supply in reverse. So why do we do that? Well, it's an EMF with no internal resistance. We treat it like an EMF in reverse because we are dropping about 0.7 volts. So we drop 0.7 volts, drop 0.7 volts. By the way, examiners in the textbook, they say 0.6. I've seen mark schemes where they accept 0.7, and it could be as high as 0.8, as I mentioned. There's no hard and fast rule about this, so you just have to make sure you state what value you're using when answering questions about this. That's all you have to do. So drop 0.7 volts across diode, and then you analyze the rest of the circuit. That's all you do. So if I've got a circuit like this, let's do a quick sketch where we've got a power supply, we've got a resistor, and we've got a forward bias diode like this. Perhaps this is a 5-volt power supply. This is 0.7 volts we drop across that. So the resistor has 4.3 volts dropped across it. And if we know the potential difference dropped across the resistor, then we can calculate the current that has passed through that resistor. We just say, okay, well, I is going to equal V, so 4.3 divided by R, whatever the resistance of that resistor is. And that will allow you to calculate that current in that situation. So that's it with forward bias diodes. Reverse bias diodes are even easier. Reverse bias diodes, they are diodes where we've connected them the wrong way round. And we treat that just like an open circuit because it's got near infinite resistance. So we treat like open circuit, i.e. infinite resistance. And what that means is that the potential difference across it is going to be the full potential difference. So if I just take something like this, our circuit that we had before, and now this time let's connect our diode the wrong way around. Whoops, I connected it back to front, just like that. Then we're going to have 5 volts on our supply. This is going to be 0 volts, that's going to be 5 volts. There's going to have to be, because it's got near infinite resistance, it's got to have 0 current passing through it. And if there's 0 current passing through that diode, then there's 0 amperes passing through there. And we know that let's say V is equal to IR. So V is equal to IR, where I is equal to 0. So there's no potential difference across that resistor. So the full potential difference is across the reverse bias diode. Only because the reverse bias diode has, let's say, infinite resistance. I think I just managed to get that little bit about diodes crammed in on the side there. Not my best work, but hopefully that's good enough so that you can solve circuits problems where there are diodes included. If you can work with power supplies, then you can work with, and cells, then you can work with diodes. You just treat the diode like a cell connected backwards so that you drop 0.7 volts across it, and you do that before you do any of the other calculations. Right, okay. I think I can stop there. We're going to move on next lesson to the last part of the electricity topic, potential dividers. I hope you join me for that. Bye-bye.